In this lesson, we're going to cover slope fields and differential equations. Our first definition is a differential equation. It's an equation that contains an unknown function and one or more of its derivatives. So here's an example of a differential equation. You have dy dx equals, and then over here we have y ln of x. To solve a differential equation or to find its solution, you're going to find the unique solution that satisfies the given conditions among the family of equations with the given derivative. This definition says, suppose a first-order differential equation is of form y prime equals f of, and then we have x comma y, where f of x comma y is an expression in x and y. The differential equation can be interpreted as the slope of a solution curve at a point xy on a curve is f of x comma y. If we draw short line segments with this slope at several points xy, the result is called a slope field, or it's also known as a direction field. These line segments or slope field indicate the direction in which the solution curve is heading. This example says, consider the equation y equals 1/2 x squared, or any of the following, where we have 1/2 x squared minus 4, 1/2 x squared plus 3, or 1/2 x squared plus an arbitrary constant c. Part A, identify the differential equation that satisfies all of the above equations. For all of these equations, when you take the derivative with respect to x, you get dy dx equals, and then on this side, when you take the derivative with respect to x, when you bring the 2 down, the 2 and the 1/2 cancel, and you're just left with x. So our differential equation is dy dx equals x. Part B says to create a slope field for this differential equation. So to create your slope field, you're looking at this equation as your slope. This differential equation is only with respect to x. Some of them will be with respect to y, and then others will be x and y. So let's look at a point on here. So let's start at 0, 0. Since our differential equation is only with respect to x, we take the x coordinate of this point and we plug it in. So again, this point right here is 0, 0, so x equals 0. When you plug it in, you get the slope is equal to 0. So we're going to draw a little line segment with slope 0 through this point. It's kind of hard to see, but I drew a little tiny horizontal line. We're going to do the same thing with all of these points along this vertical line. The coordinates of this point is 0, 1. Again, the x value is 0, so we plug that in and you get slope equals 0. So I drew a line segment with slope 0. Similarly, right here, this point is 0, 2. So the x coordinate is 0, you plug that in, you still get 0, so you draw a line segment of slope 0 going through this point. And we'll continue down here. Now if we look at these points along this line, so at this point the coordinates were 1, 0. You take the value 1 and you plug it in for x, and you get slope equals 1. And so we drew a line segment with slope positive 1 at this point. We're going to do the same thing right here. The coordinates of this point are 1, 1. X equals 1, so we plug that in, so we get slope equals 1. So we draw a line segment of slope 1 right here. And you'll notice the pattern for all the points along this vertical line. The x coordinate is going to be 1. When you plug in 1 right here, you get slope equals 1. So all of these points get a little line segment of slope 1. When we move over here, any point along this vertical line has x coordinate of a 2. So again, this point right here is 2, 0. Because the x coordinate is 2, you take the 2 and you plug it in, slope is equal to 2. So then we draw a line segment with slope 2 at this point. And similarly, at all of these points, your x coordinate equals 2. So when you plug in 2 to this, you get slope equals 2. So all of these points are also going to have a line segment of slope 2. As you move to these points, all of them have x coordinates of 3. So we're going to draw line segments with slope 3. Okay, so these all have slope 3. Over here, all of these points have an x-coordinate of -1, so we'll do a line segment of slope -1. These have x-coordinates of -2, so we'll do line segments of slope -2. And then finally, these are going to be slope of -3. And it's okay if they're not exactly perfect, as long as you get the general idea. So here's our slope field for the differential equation dy dx equals x. This example says the calculator drawn slope field for the differential equation dy dx equals xy is shown in the figure below. The solution curve passing through the point 0, 1 is also shown. So you can see this point right here is 0, 1. And then what happens is, according to the slope field, to the right, the curve is going to go up. And then to the left, the curve also goes up. Part A says sketch the solution curve through the point 0, 2. So we plot the point 0, 2. And to the right, we're going to curve up. And to the left, we're also going to curve up. For part B, we're going to sketch the solution curve through the point 0, -1. So we plot the point 0, -1 right here. And you just follow the slope field. So to the right, you can see the slope field kind of pushes the solution curve down, and then similarly to the left. And there's our final answer. This example says the calculator drawn slope field for the differential equation dy dx equals x plus y is shown in the figure below. Part A, sketch the solution curve through the point 0, 1. So we're going to plot the point 0, 1. To the right, you can see that the slope field is kind of pushing the line up. And then to the left, we're going to flatten out right here, and then we'll coast along this asymptote. Part B, sketch the solution curve through the point -3, 0. So first you plot the point, and I have it right here, -3, 0. To the right, we're going to curve down. To the left, we're going to flow up and then go along that asymptote. So there's our two solution curves through these initial conditions. Our next definition is an equilibrium solution. It's a constant solution to a differential equation. A solution curve found on a slope field that is a constant or it's horizontal. Okay, next, when you're matching a slope field with a differential equation, what you're going to do is find values for x and y that make the slope equal to 0, or you're considering horizontal line segments. For this example, we're going to match the slope fields with their differential equations. So I want to look at this differential equation, and if we were to set this equal to 0, what value would you get for x? So I have 1/2 x plus 1 and set it equal to 0. You'd subtract 1 and then times both sides by 2. So what this means is the slope is going to be equal to 0, meaning we'll have horizontal line segments along the line x equals -2. So if you look at B, at x equals -2, you have horizontal line segments. So this differential equation corresponds to graph B. Okay, next we're going to take this differential equation, set it equal to 0, and you end up getting y is equal to x. And if you look at these graphs right here for part C, along the line y equals x, you have horizontal line segments, or slope equal to 0. So this differential equation corresponds to graph C. Okay, next we're going to take this differential and set it equal to 0, and you just get that y is equal to 0. So we're going to look at our other two graphs, so A and D, and it looks like D, along the line y equals 0 is where you would have horizontal line segments. And then finally, we're going to take this, set it equal to 0, and if we multiply both sides of this equation by -y, you're going to get x equals 0. And if we look at graph A, you can see along the line x equals 0, we have our horizontal line segments. This example says match each slope field with the equation that the slope field could represent. So we're going to take this equation and take the derivative with respect to x. So we get dy dx equals, and over here, the derivative of 1 is 0. So that means for the entire slope field, we're going to have lines with slope equal to 0, or horizontal line segments. So that's going to correspond to graph C, where you can see that every line is a horizontal line. Okay, next we're going to do the same thing. We're going to take the derivative with respect to x. So dy dx is going to equal 1. So if you look at our graphs, you can see that for part D, all of the line segments are a slope of 1. So this differential corresponds to graph D. For this one, we're going to take the derivative. So the differential equation equals 2x. So I want to think about these two graphs that are left. If we think about going to the right of the y-axis, all of the x values are positive. So if we take positive x values and plug them into this, we're going to get out positive slopes. And you can see for part A and B, both graphs to the right have positive slopes. Next, if we check to the left of the y-axis, all of these x values are negative. So we'd plug in a negative value right here, and when you times by 2, you're still going to have a negative value. So that means all of the lines need to have a negative slope. And you can see for part B, to the left of the y-axis, all of these lines have negative slope. But over here, all of these lines have positive slope. So that means this differential equation corresponds to graph B. And then finally, for this one, when we take the derivative, we get 1/2 x squared. And that works out great because when you plug in positive x values, you're going to get out a positive, and all of these slopes are positive. But when we plug in negative x values and you square them, you're also going to get out a positive slope. And all of these are positive slopes. So that works out great for this. So this differential equation corresponds to graph A. This example says draw a slope field for each of the following differential equations. So for part A, we have dy dx equals x plus 1. Since this differential is only with respect to x, it works out nicely because you can think about this graph in terms of vertical lines. So all along this vertical line, x is equal to 0. So for any of these given points, if you plug in 0 for x, you just get out 1. So all along these points right here, we're going to draw a slope of 1. Moving to the right, all of these points have an x-coordinate of positive 1. So when you plug in positive 1 right here for x, you get 1 plus 1 is 2. So your slope is equal to 2. So along this line, you're going to draw line segments with slope positive 2. Along this vertical line, your x coordinates are 2. So we're going to plug in 2. 2 plus 1 is 3. So we're going to have line segments with slope 3. And over here, this was x equals 3. We plug that in and we get slope of 4. Right here, x coordinates are negative 1. So when you plug in negative 1 plus 1, you get 0. So I drew line segments with slope equal to 0. Right here we have negative 2. Negative 2 plus 1 is negative 1. So our line segments all have slope negative 1. And finally, this is negative 3. So negative 3 plus 1 is negative 2. And here's our slope field. It says use the slope field above to sketch a solution curve that passes through the point 1, 0. So we plot the point 1, 0. To the right, the graph curves up. To the left, the graph curves down, it bottoms out, and then goes up. This differential equation has x and y, so what I want to do is take this and set it equal to 0. We end up getting y equals x. So what that means is along the line y equals x, we're going to have slopes equal to 0. Next, I want to look at this line right here. This point along the line is 1, 0. X equals 1, y equals 0. So if we take x equals 1 and y equals 0 and plug it in, we get 0 minus 1, which equals negative 1. So at this point, we have a slope of negative 1. This point right here, the coordinates are 2, 1. So if we plug them in, we get 1 minus 2, and that makes negative 1. So also slope of negative 1. This point right here is 3, 2, same thing. 2 minus 3 is negative 1, and you have slope of negative 1. So all along this line, we have points with slope of negative 1. Again, I just want to point out that all of these little line segments, they're not drawn perfectly, but as long as they're in the general vicinity of what they should be, then you're fine. Okay, so to look at this, so next we have this line right here. This point is 2, 0. So if we go 0 minus 2, you get negative 2. And I just want to double check, this point right here is 3, 1. So you go 1 minus 3 is negative 2 also. And again, because this specific differential equation is following this pattern, then we can fill in these two as well. This point is 3, 0, so 0 minus 3 is negative 3. So I made all of these points have the same slope. And as you're probably guessing, these are going to get more steep, and this is going to even get more steep. Okay, so we have this side done. Let's go ahead and work on this side. This point right here is negative 1, 0. So if we go 0 minus a negative 1, that makes positive 1. And I just want to verify, this point right here is 0, 1, so that goes 1 minus 0, or just 1. So we can fill in this point here as slope of 1, and slope of 1, and slope of 1. All right, along this line right here, let's just double check. This is negative 2, 0. So we go 0 minus negative 2 is positive 2. And then you can guess these are going to be positive 3, positive 4, and positive 5. All right, and there's our slope field. This example says given the differential equation dy dx equals y, Part A, draw a slope field satisfying the given differential equation. Since our differential equation is only with respect to y, we can consider the horizontal lines. So along this horizontal line right here, all of our y coordinates are 0. Along this horizontal line, all of the y coordinates are y equals 1. And then along here, y is equal to 2. Along here, all of the coordinates are y equals negative 1. And then down here is negative 2. Part B says sketch the path of unique solution if the graph passes through the point 0, 1. So we'll plot the point 0, 1. To the right, the graph will go up, and to the left, the graph will coast along this horizontal asymptote. And here's the solution curve for part C, going through the point 0, negative 1. Part D says what family of functions do these two graphs represent? So if you look at this curve and this one, you'll notice that these are exponential functions. Part E says find a solution y equals f of x to the given differential equation satisfying the initial condition f of 0 equals 1. So here's our differential equation, and we need to find a solution in the form of y equals f of x. So that'll be y with respect to x. So our first step is we need to separate our variables. Right now we have dy and dx on the left side of the equation, and we have y on the right. What we want to do is we want our y's on the left and our x's on the right. So this is a proportion. You can think of this as y over 1. And anytime you have a proportion, things move diagonally across the equal sign. So this dx is going to come up to the right, and we're going to move this y down to the left. So you get 1 over y dy equals dx. Okay, next we're going to take the integral of both sides. So the integral of 1 over y dy is going to be ln absolute value of y. And technically over here there's a 1, so the integral of 1 with respect to x is going to be x. And because both of these are indefinite integrals, technically you could put plus c here and also another plus c here, but you could also subtract this c and bring it over and then make another arbitrary constant. So we're just going to put 1 plus c on the right. So once you get to the point where you have c in the problem, you're going to plug in the initial condition. So we have f of 0 equals 1, so that means x equals 0 and y equals 1. And by plugging the initial condition in, you can solve for c. The absolute value of 1 is 1, ln of 1 is 0, so you end up getting that c is equal to 0. Next, you're going to take this value and you're going to plug it in the first place where c showed up. And next we're going to solve for y, so we're going to get this into the form of y equals f of x. So first step, to solve for this y, we're going to get rid of this natural log. To do so, we're going to exponentiate using base e. So we write base e on both sides of the equation, and then we raise both of these sides up into the exponents. So we have e to the ln of absolute value of y equals e to the x. And so over here, these undo each other, and you just have the absolute value of y. So you end up getting the absolute value of y is equal to e to the x. Next, to take the y out of the absolute value, what you do is you bring in a plus or minus on the right side of the equation. So we get y equals plus or minus e to the x. And then finally, we just need to decide if the equation is supposed to be y equals positive e to the x or y equals negative e to the x. And to do so, you're checking the initial condition of f of 0 equals 1. So because this f of 0 is equal to a positive 1, that means we need to use the positive option. So again, you want to check which one of these satisfies the initial condition f of 0 equals 1. So I plugged in 1 for y right here, and then plugged in 0 for x and used the positive option. And you get that 1 is equal to 1, so that works. Therefore, our solution to the differential equation that satisfies the initial condition f of 0 equals 1 is the equation y equals e to the x. Alright guys, thanks for watching!